we talked about this, that if you have a multi-class classification, you can always treat it as a sequence of binary, right? What does it mean? It means that I should start by saying that, okay, I'm going to classify 0 or anything else, right? If it's 0, classification is over. If it's not 0, then I have another classifier, right? It's going to tell me 1 or anyone else, right? And so on towards the end. But if I want to do that, it means that I need to have a sequence of neural networks, right? So I have one neural network, one classifier, which is just classifying between 0 and the others. The next one, which is classifying between 1 and the others, and so on, right? This is not practical, especially if you have so many labels, right? Classes, sorry. So this is not a good idea, but indeed, the way that we treated the output in the binary classification could give us some idea on how we can do a classification on multiple classes. Any idea you have how we can do it? Like if I look at if I want to just describe the output, and I want to describe it in a way that is smooth, it's differentiable, yeah?
Just like
probability of all the classes, right? Exactly. So the best way that you can think of it is, again, if I have 10 classes, maybe I can find a probability vector with 10 different entries. And these 10 different entries, all of them add up to 1, so they are probability. They are all between 0 and 1. And each of them is giving me the chance of that input is for the particular class, right? Class 0, class 1, till class 9, right? So you can treat it this way. And again, this is going to be a kind of extension to what we have done in the binary classification. And this is eventually what we do in practice. So what we do, we would say that, OK, let's say that we have these 10 different classes from 0 to 9. We want to classify them. And the way that we treat it, we just simply compute the probability of each class happening given the image that we have, right? So this was the neural network that we had in the binary classification. You give your input in the first layer. Your image goes in. You compute. At the output, you get y3, right? So y3 is the probability of your label being 1, right? What is the probability of your label being 0? 1 minus y3. So eventually, it's true that you're computing only y3, but you can think of the output in this form. So you have 1 minus y3 and y3, right? You have such probability vector, right? And y3 is something between 0 and 1. So both of these numbers are positive. They add up to 1. This is a probability, right? But we did not write this guy down anymore because, well, when we know this, we do know that one as well, right? Everybody's clear, right? Now, what you can do, you can just think this way, and now you just extend it for C different classes, right? Say I have C different classes, class 1 to class C. In this particular example that we consider, we have 10 classes, 0, 1, 2, till 9. And then you can just compute, instead of computing these two numbers, you can compute C different numbers, right? So if we think of the MNIST classification, we are going to compute y3 of class 0. So this is the probability of my image being 0, right? y3, 1. This is the probability of my image being 1, and so on till y3, 9, right? So this is the chance of my image being of class 9, right? Now, if I add up this guy, this should be what? 1, of course. I mean, my image is one of these guys, right? So this should be 1, and all of these numbers should be something positive, right? Because it's a probability, correct? So if I can come up with some sort of solution, some sort of function, which going to look at the last layer output. So this is look at the previous layer. So it's going to take whatever was at the last hidden layer, and then it's going to compute me C different, in our example, 10 different probability values, then that's it, right? Everybody's cool, right? You got the idea. OK, that's cool. This is what we call it actually vector activation. Why I call it vector activation? Because when you look at this this block here, the block which is computing the probabilities, this is one giant block, right? You cannot write it down as separate blocks, right? Because it needs to compute all probabilities together, right? The first entry, second entry, till the last entry, they are not computed independently. If you compute them independently, then there is no guarantee that they add up to 1, right? So you need to compute them all together. You see it, right? So you need to compute all of them together. So the thing that is happening is everybody from this hidden layer is going to that guy. That is again like a neuron, right? It's getting all the information, but it's not computing just a scalar, right? It's computing a vector at the output, right? Clear? This is what we call it a vector-activated neuron. This is essentially the idea of basic artificial neuron. You just replace the output to be a vector. Everybody's clear? Okay, so the way that you compute it typically is that, since it is neuron, definitely it's going to consist of two components. One activation and one soft linear computation, right? So you're going to get your x. X is the thing that is coming inside your neuron. If you look at this image, what is x? What is it? This last layer, right? By x, I don't mean this guy. By x, it's a bit confusing because I have notation x here, but this is image, right? I'm talking about this particular guy, right? X is the one which is going inside it, right? So in this particular example, this is the output of last hidden layer, right? So you have computed a bunch of things at the output of your hidden layer, right? Now from that one, you want to compute a probability. What do? You get that guy, you multiply it by a matrix, right? So if you remember, in the single neuron, what we do instead of having a matrix, we are going to have a vector, right? And then we do inner product because at the end we need a scalar, right? But now I need to have a matrix because I want to get a vector, and I just convert it to another vector, right? Now, say that the input x is n-dimensional. So that vector x that you see inside the argument, x, is n-dimensional, okay? Forget about b right now, the bias. Forget about that one. I want to just multiply it to a matrix to compute something at the output. I'm going to call it z, okay? Now, this z is the one which is later going to get activated to give me probabilities, right? So, dimension of this z should be c, right? Exactly same number of classes that I have, because I want my probability to give the chances over the classes, right? So this guy, z, should be of size c, right? What should be the size of this matrix W then? It's going to be c times n, right? So this is going to be one object which is matching this guy, this x. It's going to get multiplied with this one, and it's going to give me the object that I want, right? So it's exactly as before. Like if you think of a basic neuron, this value c here, the number of classes is simply 1, right? And then this matrix is simply 1 by n, which is a row vector, right? And then you get back to a normal neuron, right? Okay, so this guy is the matrix. Now, I'm going to have one bias as well because, I can shift everything linearly. Now, if I consider the bias here, what is the dimension of this bias? It's again c, right? Because it should match this guy, right? So this bias is again a vector here, and then this guy is going to add up to this one. This thing that comes out of this guy, this argument, is the linear transform, is the z variable that we always have before activation, right? And now that you have it, you're going to have this function f, right? And this function f going to get this c-dimensional vector and convert it into another c-dimensional vector. Now you might tell me, okay, this is like one layer because you're going to have I'm activating c different values, but there is one key point here. The key point here is that this f is not computing every single output from the corresponding input. It's computing every single output from all the inputs. And I'm going to give you the example of softmax. You're going to see it. Okay? So this F here is not necessarily computing every single entry of the output from the corresponding entry in the input, because if this is the case, then it's going to reduce to the classic layer of a neural network. So this is the first point. One thing that we can do, and I'm going to do it from now on, so we have done it a couple of times. We really don't need to care about this bias. We can add this dummy 1 here, and we can think of the whole process inside the activation function as one linear transform, one giant linear transform, right? So as I said, you don't really need to care about this. The only thing that you should be sure about is that you have always one linear transform which gets one object and transform it to another object that you want, right? And that guy is W. Now this W is getting multiplied with X, so it's going to just linearly transform, and then we are going to activate it, right? So now, if you want to think about it in terms of computation graph, again, everything just can be represented compactly. You can think of your X to be the input that is going inside this layer. You first linearly transform it, so you're going to get Z. This Z is exactly of the dimension of the number of classes that you want, and then you activate it using this vector activation function, F. Okay? Questions? Everybody's cool? No. If you can, this W also includes bias, right? Right. Yes. Different. Sorry. N. You mean the size of X? N here. N is the size of this guy, size of this layer, whatever you have at the output, right? So you have n-dimensional thing coming out of this guy here. So these are the features computed by your last layer, right? And then you just transform it into the dimension that you want, which is C, and then you activate it all together, right? Exactly, right. So what you should always think, like here, this guy is of the same nature of what you have here and here, right? These are better, like a filtered version of this guy, right? The guy who is doing the classification at the end is just this last layer, right? Yes?
So, the last classification layer is sort of like making like 9 neurons.
Not,
all have the same weight. Like, so like the previous layer for it has like a 9 connection to each neuron, but I don't calculate the weights independently. They're all have like the same weight.
Oh, no. It's not the case. You mean 9? You mean based on this one 9? Number of classes, you mean? By 9, you mean number of classes, right? Okay. Now, I guess here is 10, right? 10 classes. Okay. So you have 10 classes, right? And you have your input, right? But what you want to do, you want to compute exactly 10 different entries, right? So the number of weights that you have is not different with the case that you have 10 different neurons. And all the weights are not the same. They are different, right? Yeah. But the only difference is that once you computed these 10 different values, you are not sending every single through one activation. You just send all of them through one giant activation, which compute the 10 outputs together. And I give you the example of softmax. You see the difference there. But then in terms of the number of weights you have is the same thing as before. Okay? Clear? Okay. Questions? No question? Okay, good. Now, one of the most famous ones, which probably most of you have heard of, is softmax, right? Softmax is a vector activated neuron. Now, one thing that you should pay attention here is that some people call it softmax layer. It's okay, you can say it, but technically it's not a layer. It's just one giant neuron, right? Because it's not consisting of multiple neurons, right? This is one giant neuron. What does this softmax do? This softmax is going to compute the output in terms of the linear transform. So Z, what you see as Z here, is what you already have linearly transformed. Z is this guy, you see? So you got your input, x, the features of the last layer. You linearly transformed it into z. This z is of the same dimension as the number of classes you have, 10 different entries, right? And now, out of this 10-dimensional vector, you want to compute another 10-dimensional vector. Now, the thing that you do is that you compute every single entry to be e to power corresponding entry of z divided by sum of e to power all z's. Okay? You see it? Now, here, if you think of y1, the first entry in y, okay? Is y1 only depending on z1? No, it depends on z1 and z2 and z3 till the last z, right? What about y2? Same. y3 is same, right? So you see what I mean by vector calculation, right? You cannot say that if I want to compute y1, I only need z1, right? This is not the case. You really need to know z1 till zc to be able to compute y1, right? Same for y2 everybody, right? So it's not anymore c different neurons, right? This is one giant neuron looking at all c values and computing c new values for you. Everybody's cool? Clear? Okay, now, why do we have this guy? Any idea why we compute this one? Yes? It adds up to 1. It's like a probability, right? So if you look at this guy, first of all, every single entry of y is positive, right? Definitely. Because exponential function is always positive, right? Now, every single entry is between 0 and 1 as well, because a nominator is always smaller than denominator, right? Denominator is nominator plus a bunch of other terms, right? So these are numbers between 0 and 1, and the cool thing about them is that if you add them up, they are going to add up to 1, right? So if I add them up, I am adding up this term, right? But the denominator does not depend on the summation, right? Denominator is the same for every single entry, right? So the summation goes in nominator, then you have same thing in nominator and denominator. It adds up to 1, right? So this is a probability distribution, and because of that, we are interested in such a activation, right? Now, you might come up with your own way of computing probability distribution. In the assignment 2, you're going to see one example. They are dummy examples usually because they are having some troubles in terms of gradient and other things, but the only main reason that we are just computing softmax is because we want the probability at the output, okay? But among the choices that we had up to now, softmax was the most stable one. This is one we are sticking to this one. So now, the thing is that if I want to do multiclass classification, I can use the same architecture as before. Now, instead of having the last layer being a sigmoid single neuron, I can just put a vector-activated softmax layer or softmax neuron there to compute the probabilities, right? So this means that I have the same architecture as before. My image goes in. It's going to get computed in the first layer. I get a bunch of features. Those features, again, get processed by the second layer. Then again I'm going to get a bunch of other features. Now, this last feature, instead of computing one single probability out of it, I just give them to one softmax, right? And that softmax is going to compute me c different probabilities, right? And then I would try my best that the probability of the corresponding label for the input is the highest, right? So that I'm going to conclude at the output that this is that particular image, right? Everybody's clear? Now, one thing here in this layer that you see, this last layer or these edges connecting the last hidden layer to the softmax. What do we have weights? Yes, right? We do have weights, right? There are a bunch of weights also here because this softmax, before computing that probability, it needs to get the output of last layer, linearly transforming that matrix W that I told you, right? And then out of that 10-dimensional, c-dimensional z, it's going to compute your probability, right? So you are still doing the same thing as you had one layer here with C different neurons, right? The only difference is that you are not activating them separately. You are activating them all together with one softmax function, right? Yes?
How do you know if a neural network is fully connected or not, or should be fully connected?
Oh, here, when nothing is indicated, then it's fully connected. Okay. Yeah. If it's not fully connected, then you need to have a sort of architecture that explains how you're dropping connections.
Like the XOR, it's not fully connected, right?
XOR is fully connected, the one we designed. Is there any neuron that is not connected to the other? All of them are connected.
When you do multiple XORs?
Oh, that one, yes, that one. Yeah, but even there, you can just think of connections which you are not writing it down. You can think of those connections being 0, right? If you start, yes, but the key point is that when you are training this guy, you don't know what should the weights be, right? In that example, you do have the knowledge in advance. You are not training anything. You are just building the neural network, right?
If we were to train it, it would just be
Yes. If you had this magic trainer which can work with perceptron properly, then it's going to end up them being 0, the other ones being the right weights. Okay? Questions? No question? Okay. So, yeah. Now, one thing here, if you want to, again, when you have the softmax here, you're going to have the same sort of computation graph for forward propagation, and then again, if you want to do backward propagation to compute the gradient, things going to be the same as before. So here you again have your image. Going through the first layer, you're going to get Z1. Z1 gets activated. You get Y1. Y1 is the first set of features you have in your neural network, right? You would say it's not enough. It's not a good set of features. So I'm going to get Y1. Again, linearly, you transform it to Z2. You activate it. You get your Y2, right? If you need more, you're going to do it in more layers, right? But once you're over with these processes, then you're going to get this Y2. You linearly transform it. You're going to get your Z3. And then you do softmax in order to get your final output. That final output is the probability of every class for this particular image, X. Clear, right? Everybody's cool? OK. Now, this is the same kind of computation graph as we had before. The only difference to the binary classification is that, first of all, here we are not doing anymore one single computation. So you're not getting a scalar output, Z. And then the other thing is that you have soft max, which is not entry-wise activation anymore, is a vector activation, right? But the rest of it is same as before, right? OK, cool. Now, well, if you think in terms of forward propagation, same thing is going to happen. The only thing that is different is that in the last layer, you are going to get C different outputs, and you activate them by softmax. So it's the same thing as we talked before. And now the question is that how you can compute the loss between the output of this neural network and the true label that you have inside your data set. Any suggestion? So if the true label is, let's think in terms of MNIST. So look at this guy here. So we have 10 different classes, right? It could be 0, 1 till 9, right? If your label is 1, if your image is the handwritten digit 1, what do you like to see at the output? Everybody's 0. This guy is 1, right? You want to see this, right? And you cannot see it for sure, like exactly like that, because your softmax is not giving you 0 or 1 exactly, but it can get close to that, right? So you want this to be, for instance, 0.99999, and the other ones to be 0.0000 something, right? You want to see something like that, right? Now, if you want to do that, this means that you do know the true label, which is 1, and then you want this guy to be large, and these guys to be small, right? Now, you can again do the same interpretation as we did in the binary classes. What you can say if I have one particular image, then I can think of that image having a probability distribution. Probability P1 is the chance of that image being in class 1, P2 is the chance of that image being in class 2, and PC is the chance of that image being in class C, right? Now, if you know what is the class of that image, how does this probability vector look like? If you, for instance, have one particular image and you know that its label is V, for instance, V is 1, what do you say? How does this probability vector look like? Everybody's going to be 0 except the corresponding label, right? So if my label is V, then I would say, what is the chance of my image being class 1? It's 0. What is the chance of my image being class 2? It's 0. What is the chance of my image being class V? It's 1. What is the chance of the rest? Is 0, right? So you can always think of it in this form, right? So again, when you have the label, you have the true value of this vector, and that one is a vector with everybody 0 except the true label, right? Do you know what we call that vector? One-hot vector, right? So this is what you call it, one-hot vector, right? So the true label is always a one-hot vector, which you can always write it down based on the label you have inside your data set, right? So if your image is label 1, then it's a one-hot vector with the entry 1 being 1, anybody else being 0, right? So in general, you're going to write it down 1v. So this is the vector of everybody being 0 except one of them. And the one which is 1 is actually the one with label v, with index v, right? So for instance, if you think in the case of 3 classes, 1, 1 is the one which has the first entry 1, the rest 0. 1, 2 is the one which has the second entry 1, and so on, right? Everybody's cool, right? So, moral of the story, when you have your image, you eventually have a sample for that probability vector, right? Image is handwritten 0, then the true label is a vector with the first entry being 1, the rest of them being 0. And the thing that you need to do now is that you look at the output of your softmax and you try to make it as close as possible to this one-hot vector, right? So when the true label is 0, you look at the output of this softmax vector, right? And then you try to make this guy close to 1, anybody else close to 0, right? Now, if you come up with any loss function which does that for you, that's acceptable, right? One case is that you simply use the basic MSE, right? The MSEs that we said. Because if I just subtract this guy from the true one-hot vector, then the corresponding vector, when I minimize it, the corresponding entry is going to get close to 1. The remaining entries are going to get close to 0, right? And that's it, right? A better solution, you might guess, is the cross entropy, and this is what we do it in practice. So this is the case when you consider MSE. So you would say, let's look at the output of my neural network. This output is the output of softmax. It's going to have C different values, right? And I'm going to subtract them from the one-hot vector, right? The vector which is 1 exactly at the corresponding class, and the true class, and 0 everywhere else, right? Now, if you think that your label is V and your output is Y, then the thing that you're going to see is going to be of this form, right? Because YC, for any label but V is going to be subtracted from 0, right? Correct? So you're going to have YC squared plus Y of that particular label, which is the true label, minus 1 squared, right? Now you look at this loss function. This makes sense that if you minimize this one, you're going to cover the correct label, right? When you minimize this one, you make Y of the corresponding, the true label, to be close to 1, the probability of the true label being close to 1, and everybody else being close to 0, right? Right? So this is the case when you are doing MSE. You are using MSE for loss computation. And the key point about the MSE is that it has a gradient, right? If you want to compute the gradient, what would be the gradient? The gradient of your loss is going to be the partial derivative with respect to first entry, right? So you look at this term. The first entry probably is the first one, which has only y1 squared. So it's going to be 2 times y1, right? 2 times y2. The only guy which has different term is your true label term, right? 2 times yv minus 1, right? And you can again simply write it down in this form, right? Everybody's clear? Now, one of the reasons that people used to call backpropagation because they were thinking of it as in terms of error propagation. And you can see this here, right? This is your output. This is what you want to see. You're computing the difference. That is the gradient, of course, right? But it looks like an error term, right? And then you pass it backward in your neural network, right? So it's like you are just passing backward the error, and using that, you are finding a way to update your weights, right? It's an intuitive way of interpretation, right? And this is why people used to call it backpropagation, because they felt like we are backpropagating the error, right? We look at the error at the output, we just tell the network, oh, you have this much of error, change the weights, right? But basically, you are doing gradient descent, right? Okay, so this is the case when you have MSE. You can also have the cross entropy. Before I show it here, any idea how I can compute the cross entropy? Say I have this output. This is the output of the softmax. And the true label is 0. How can I compute the cross entropy? Any suggestion? The cross entropy is always proportional to the logarithm of 1 over probability, right? So what do you choose? If the true label is 0, say I compute log of 1 over y0, y3, 0. Is it a good choice of loss? If I want to minimize it, what should I do? This guy should go close to 1, right? Because when it's smaller than 1, the smaller it gets, the larger this one would be, right? When it's close to 1, this is going to be 0, right? Everybody's cool? Right? Then, if this guy is close to 1, what's going to happen to the others? 0. Do I need to care about them anymore? No, right? So this is going to be your loss. If you do know what is your label, right, you're going to look at the output at that label. You compute log of 1 over that output. Okay? This is what would be the cross entropy in a general case. So people write it down in this form. So they say that we have the one-hot vector. We inner product it with the logarithm of 1 over the output of softmax, right? They say it. But of course, when you have a one-hot vector, this one-hot vector is 0 everywhere, but at the place of the true label, right? So that whole summation is going to just remain with one term, right? And that one term is the output of the softmax corresponding to the true label, right? Meaning that you look at the softmax, you look at your true label. Your true label is 1. You look at the entry of the softmax which corresponds to label 1, and then you compute log 1 over that guy, right? Because you want to make that guy close to 1 and everybody else close to 0, right? Everybody's cool? You see it? Yes? This one here? Yeah, I mean, you could potentially drop these guys as well. You mean that, right? So you,
I'm just wondering, why do you do the inner product in the cross entropy?
inner product, this one, but this inner product is not the real inner product. It's just an indicator, right? It's just telling you, just select which guy, right? This is not really the correct, because you can have y and one other vector, right? And that vector, instead of being one hot, it could be a probability distribution. And if you,
Why don't you do the difference between the difference of the entry wises, the label and the one hot and the
but you're computing log, right?
yes.
Yeah, you cannot do that with log, right? Yeah. But the reason that we do, there is a more general definition of cross entropy, which is proportional, proportional to the KL divergence between the two probabilities. And then if instead of one hot vector, I just replace a general probability vector, which is having C different entries, all of them between 0 and 1, adding up to 1. This is one general vector. Then the cross entropy is not going to be defined this way. I mean, like here is going to be the probability of the corresponding entry, right? And then that one is like related to the KL divergence, which is the difference between two probabilities, right? And that is a very strong metric of difference for the probability space. But we don't want to talk about that here because the reason we are using it here simply is this one, right? Because we are just trying to push our particular probability there. But theoretically, you could say that this guy is a stronger metric of difference between the two distributions as compared to the previous one. And because of that, this converges better. Yeah. Questions? Yeah. Previous one? Here? Here you are looking at your output, and then you say, and you compare it to the corresponding one hot vector. And you just subtract them and add up the whole error term. Say, for example, your true label is 0, okay? If it means that V here is 0, or 1, say. So it means the first class is your true class. Like the image that you are classifying is coming from class 1, right? So if you put 1 here, V equals by 1, then you are looking at your output, Y, the whole vector. But that vector is C-dimensional, right? Now, the first one, you compare it to 1. So you subtract it from 1, you make it a square. For the other ones, you just square them, right? Now, when you minimize this one, everybody who had no subtraction going to get to 0, right? And that one, which was subtracted from 1, is going to get close to 1, right? If you want to minimize it, if you want to minimize this summation, I mean, definitely all terms should be 0, right? And then the only term that is going to, the vector which is going to minimize this term is when Y for every label is 0, but the true label, right? This term cannot be negative, right? And so the minimum value it could take is 0, right? And then it's going to get 0 when you have these terms which are not the true label, the wrong labels. 0, and this one is 1, right? And this is exactly what you want, right? You want the probability of the true label be 1, everybody else be 0, right? So you can look at it this way, but the other thing is that you know the true probability vector, which is one hot vector. You look at your output, you just try to minimize the difference between them, right? This is one other way of thinking. Questions? No question? Great. So if you got no question, then again, here in this particular case, you are able to compute the gradient. Gradient exists. That gradient is eventually going to be of this form. As you can see again, this particular gradient is not going to be 0, right? Because your Y is not going to get anywhere close to infinity, so there is no reason for this term to be 0. And this means that you have a good gradient always. Especially when Y is very small, then this term is going to be very large. You have large gradients moving backward, telling your neural network to go towards the right direction, right? So this is a very good kind of loss. Question on that? No question? Yeah.
At what step and how does our data split into like C different classes?
Sorry?
At what step and how does it split into like C different classes?
Oh, that is given by your data, right? So for example, in MNIST, you know that your image is coming from handwritten digits 0, 1 till 9. So you do have it. If you are building your data, then you need to just specify your classes. So this is not a part of design. This is a part of data. Yeah, right, right. But when you start with the classification problem, you know that you have C classes, right? And if it's a practical problem where there could be samples from totally something out of this scope, you know, you always consider one class, which is like the class of, like out of distribution class. So you would say, I am thinking about handwritten digits, but maybe wrongly there had been some nonsense images also inside. And then there is one class for these nonsense images. Okay. Now, if you got no question, then let's just think a bit about the backpropagation. Let's say that I have put this neural network as we have. I have put softmax here. And now what I want to do, I want to put one image. I go forward. I compute the loss. And then I just move backward to compute the gradient, right? So if I go forward, I mean, that's easy, right? Like I put the image here. I do all these computations. I specify my loss. Probably I choose a cross entropy. And then I am able to compute the sample loss, right? But now that I have the sample loss, I want to move backward. The first step is quite simple, right? Because my cross entropy has a gradient, right? I compute the gradient. I just move it backward, right? Next thing that I need to do, what is it? I need to get from y3 back to z3, right? And this means that I need to have the derivative of y3 with respect to z3, right? So this is something that we have not yet talked about. I guess you can think how you can define it. But right now, let's just leave it as a question mark. So we're going to find it out. But once I have done this, the rest of it is clear, right? Because once I got to this point, like I know the gradient of the loss with respect to this node, then the next gradient is going to be simply a linear transform, right? Everything is as before, right? This is a backward transform. This is activation, again, backward transform, activation, and so on, right? So I'm going to have a linear transform. I get back. I get entry-wise activation, go back, and so on until I get to the very first layer, right? So everything, we can do it based on what we did in the basic MLP backpropagation. The only thing that is left as a question is this guy, how I can get the gradient of the output of the softmax with respect to the input of the softmax. Everybody's clear? So now, the reason that I put it here for you is to just give you again this hint that when you get into such a thing, you can always get rid of everything around it, right? So you don't really need to think globally. This is the whole magic of the backpropagation. You just need to figure out how you can resolve this issue locally, like how you can get from y3 to z3, right? Because backpropagation is just a series of local operations, right? Now, if you want to think about this problem, for instance, what you can say, you could say that, okay, I have my particular loss at the output, and I do know what is the gradient of that loss with respect to the node y3 now, right? Now, what I want to do, I want to know how I can get from the gradient of loss with respect to y3 to the gradient of loss with respect to z3, right? So you can clean up this whole graph, and you can simply think in this form again, right? Always you can think in form of a local operation. You could say, oh, I had the loss, and I do know how I can compute the loss. I do know how I am activating, so this F here is eventually our softmax, right? So we had a Z. We just activated it by softmax. We got Y, and out of Y, we just computed the loss. Now, we are able to compute the gradient of loss with respect to Y. We don't know what is the gradient of the loss with respect to this Z, right? You write it down. You just then use what? Chain rule, right? So let's do it together, and then we're going to have a break. So this is the kind of guy that I have, right? So I have C different inputs for my function. Then this function is giving me C different outputs. If I want to think about a gradient, how does that gradient look like? What kind of object it should be? Yeah. Go ahead. Exactly. So how many elements we have? How many derivatives we're going to have? C by C different entries, right? So you have y1. This is a function of everybody, right? So y1 has a partial derivative with respect to z1. y1 has a partial derivative with respect to z2. So till the last one, right? y2 has partial derivative with respect to y1, and so on till z1 till zc, and so on, right? So every single entry at the output has its own gradient with respect to everybody in the input, right? correct? And then you're going to end up with C by C array of partial derivatives, right? Now, like in linear algebra, what do we call it? Jacobian, right? But you can forget about it, right? Because who cares what we call it, right? This is one object which contains derivatives, and you do know how many derivatives should be there, right? So we call it Jacobian, of course. Like every single entry of the output has its own gradient, and you can define this Jacobian. So the Jacobian of the output with respect to input is basically you take the gradient of the first entry, second entry, till the last entry, right? And you can simply write it down in this form. So basically the array of all possible partial derivatives, any output with respect to any input, right? Then you have this guy. You want to just move backward, right? So the thing that you can think of here, so before we do any calculation here, what do you think? What should I do? I am getting from this loss here, right, to this guy y, right? How many entries this gradient has, the gradient loss of loss with respect to output of the softmax? C different outputs, right? C different, sorry, entries, right? Everybody's clear? Right? Because y is a c-dimensional vector, and then when you compute the gradient, this is a c-dimensional vector as well. What about the gradient with respect to z? What is it? It's again c-dimensional, right? Because z itself is c-dimensional, right? Z has gone through lots of processes, gave you this y. Now the gradient of, r, this loss. The gradient of the loss with respect to z is again c-dimensional, right? Now you want to get back from a c-dimensional to another c-dimensional. What should you do? Your Jacobian is c by c. Somehow you need to multiply that Jacobian into this gradient to get back to that gradient, right? This is going to be that one, right? Now, how exactly the product look like? Well, practically, you don't care. You ask PyTorch to do it, right? Technically, if you want to find out, you can start writing down the chain rule, right? So you would say, well, I want to know what is the partial derivative of my loss with respect to one single z, right? What do? I write down the chain rule. So I have the gradient, the derivative of my loss with respect to every y that I had, right? And then I multiply that one with the derivative of that y with respect to the z that I'm looking for, right? So you can start opening this up, right? So these terms, when you look at them, these are going to be one column of your Jacobian matrix, right? And then you would say, okay, I have one column of Jacobian getting multiplied with this one. So this means that this whole gradient of r hat with respect to z, oh, there is a typo here again. So it should be equal to. So between this gradient and this vector, there's equal to, sorry. It's a typo here. So the gradient with respect to z is the gradient with respect to y times the Jacobian of y with respect to z. I transpose it because I found out that I should transpose it here, right? So if you ask me by heart, I don't know it. I need to open it up, okay? But you don't care. What we're going to do from now on, most of the times, is that I'm going to write it down this way. I would say that, okay, let me just, I would do it this way. So I would just write it down that I want the gradient of r hat with respect to z. So I do have the gradient of r hat with respect to y. I need to multiply it with the gradient of y with respect to z, right? So this is the way that I'm going to think all the time, right? And what is this product here that I'm showing by circle? Well, you need to figure it out if you are really going to write it down. If you're using your packages on computer to do it, it's going to figure it out by itself. But the key point for you is that nothing else is going to happen. There is always one gradient, one derivative here getting multiplied with another derivative, right? And you can always do it, right? There is no way, no computation graph that you cannot write it down for it. Everybody's clear? Okay, so if we just consider that one, then everything going to be simple. So this backpropagation through the vector activation layer is simply just done by computing or multiplying a Jacobian, and that's it. You have the backward pass for that particular link as well on your computation graph. This means that you can simply think about the complete backpropagation. So this is going to be your complete backpropagation. Looks messy, but everything is just simply chain rule, right? You start with this gradient, this loss, you compute the gradient, you just go backward. Every time you compute the gradient of the output with respect to input, and you can compute all of them, right? And then there is always a way to multiply these guys to keep the dimension right and go backward towards the very input, right? Once you got to the input, then that's it, right? You have all the gradients, and you can compute the derivative for every single weight that you have inside your neural network.